Thank you. So yeah, I'm Maria Vincenzi. I'm a starting Einstein Fellow at Duke University. And today I'll talk about the latest supernova 1A cosmological results from the Dark Energy Survey. And so since I'm kicking off the second cosmological set of cosmology talks, I thought it was just good to spend 1 minute to kind of remind ourselves what are the big questions, open questions of modern cosmology. So I put here a very simplified timeline of the history of our universe from the Big Bang, recombination, and the following 13 billion years of cosmic expansion. So what is kind of nice about our universe is that it looks like we have a model, a very simple model called lambda CDM, that depends on just 6 free parameters, but describes very well the expansion history of our universe. It works remarkably well in describing the statistical properties of the CLV, but it also describes super well the expansion history of the subsequent 13 billion years, no matter what probe you use, supernovae, VAO, weak lensing. This lambda CDM model is built off directly from GR, and it has been one of the most successful models in modern cosmology for the past 15 years. So it works, but it kind of leave us with this rather unsatisfying picture of having a universe that is filled mostly by this dark energy, which is a form of energy we understand very little about. And this kind of mysterious nature of dark energy often called into question whether the problem is at the foundation of lambda CDM. And the problem is that GR actually doesn't work at the cosmic scales. And another crack that I should mention about lambda CDM is that it kind of fails the most basic test, which is predicting how fast the universe is expanding now. So if you take the CMB, assume lambda CDM, and measure how fast the universe is expanding, this measurement is in 5 sigma tension with what we can directly measure. And this so-called H0 tension that also Justin and other people mentioned is kind of becoming a big deal. And if you look at the archive, I think there are roughly 15 papers every month about H0. So these are kind of the big open questions about modern cosmology, and are the kind of things I'm interested in investigating with my research. And it's kind of a pretty exciting time to be working on these topics because billions of dollars have been spent and are still being invested in kind of designing experiments that can answer exactly these questions. And here I put some of the ones I've been briefly talk about in the talk. So as I mentioned in the beginning, the kind of tool I use to answer those questions are supernovae 1A. So supernovae 1A are the thermonuclear explosion of carbon-oxygen white dwarf. We don't know very well what is the exact progenitor and explosion mechanism, but what we know is that their intrinsic peak brightness, so when they reach their maximum luminosity, their intrinsic peak brightness is remarkably homogeneous. And this means that you can use supernovae 1A to measure very accurately cosmic distances. So if you have a set of supernovae 1A, you can very well measure the distance, you can spectroscopically measure the redshift, and you can basically directly trace the expansion of the universe. So you can take your data point and fit your favorite cosmological model and constrain, for example, if you assume lambda CDM, constrain how much dark matter and how much dark energy is in the universe, or you can test whether dark energy is a constant or there is some time dependence. So if you didn't remember anything about type 1A cosmology, this is kind of your cheat sheet, and you can kind of see how we use this tool and how we get to the cosmology. So one of the experiments I work on the most since day one of my PhD is the Dark Energy Survey. The Dark Energy Survey, I think it's fair to say, has been the most important cosmological ground-based experiment of the last decade. And here I put a picture of the DES Supernova Working Group. I had the privilege in the past 2-3 years to leading the analysis together with Dylan Brown, also a former Einstein Fellow. And we took this picture, I think it was last May. You can see a lot of pretty excited but exhausted faces. This picture was taken a few weeks before we kind of, after years and years of analysis, we said, we're done. We draw the line, we're done, we wrote the papers, and we can finally look at the results. Because something you might not know about cosmological analysis is this super important but super torturing thing that we call blinded analysis. So you spend years and years doing your entire analysis until you say, I'm done. And then it's when you can look at the cosmological results. And this is kind of a very important way of conducting this high precision cosmological analysis, because the idea is that you don't want to bias yourself towards a certain result you're expecting. So just to kind of give you an idea of how the dark energy supernova program impact our field, I wanted to put here the redshift distribution of the largest high redshift supernova sample using cosmology. This includes 1,300 supernovae and kind of is a combination of all the most important supernova cosmological surveys of the past 15 years. And this is what DAS measured. So roughly 1,600 high redshift supernovae. And this is the largest and deepest supernova sample ever compiled from a single telescope to date. And here is how the distance and redshift kind of diagram that I was showing in a cartoony version earlier looks like for DAS. And I think, well, I could spend hours talking about how we arrived to this plot, how the distances were measured, how the data were analyzed. But I think I decided to focus on two aspects that, listening to the talks in the past days, I thought probably are more interesting for the people in this audience. So the first thing, many people in their science are starting using machine learning. So I thought I would mention that in our analysis, machine learning was one of the key elements. You might have noticed that in this plot, all the data points are kind of color-coded. And the color bar is basically, for each supernova, its probability of being a type 1a. So what we need to use is these machine learning classifiers that can tell us, given the light curve of the supernova, how likely it's the light curve to be a type 1a supernova and not a core collapse or other type of transients. A big chunk of our analysis was to demonstrate that these classifiers are accurate enough to do high precision cosmology. Because as you can see, this contamination from non-1As can kind of bias our results. So we tested various of these algorithms. We identify the ones that are more accurate and that can be safely implemented in this analysis. But one thing I wanted to mention is that this kind of transient classification is a super active area of research in our field and in general in transient science. Because as our experiments become bigger and bigger, we need to rely a lot. Any scientific analysis of these transient data sets need to rely a lot on this classification. So if you have thoughts about this, I would love to hear them. The second aspect I want to talk about, I hope will kind of interest the people in the audience that study the research on stellar astrophysics, white dwarf astrophysics, dust. So perhaps the biggest headache and challenge for the DAS analysis was modeling the so-called supernova 1A intrinsic scatter. So this might be something a bit subtle. So here I put the residuals from our best fit cosmology. And you can see that there is a lot of scatter in the residuals, some are due to observations, but there is this kind of 10% unexplained scatter that is basically telling us that there is something that alters the brightness of our supernovae 1A that is not just the fact that we have observational noise. And this can have two origins. It's either extrinsic origin, so supernovae 1A are all born equal, but then there is dust on the way, and this kind of changes things, add a little bit of scatter. Or it can have an intrinsic origin. Supernovae 1A are not exactly all born equal, just because we have different progenitor systems. So for now, our best bet is dust, actually, because we see that this scatter kind of increases as you steer redder objects. But we spend lots of time trying to model this, and there are still some open questions. And one of the biggest challenges was how to kind of propagate uncertainties on these kind of open questions to our cosmological results. So after the analysis, tada, this is the cosmological results that we unblinded a few months ago. And as you can see, I put the supernova contours, the CMB contours, and the intersection between the two. And guess what? We find results that are consistent with lambda CDM. So the DEF supernova sample is not telling us the lambda CDM is broken. Now in the last 2 minutes, I'm gonna just briefly talk about how this next generation of experiments are gonna help us kind of advance in our field. And I'm literally gonna spend 30 seconds on each of them. So Euclid, I'm sure you know, it launched this summer. We are in science verification phase, and supernovae are not one of the scientific focuses of Euclid, but you can still see for free, just observing repeatedly some patches of the sky, you can still discover transients, and actually we have already started discovering transients just in the science verification phase. And Euclid will give us amazing supernova data in the near infrared, like space quality. And this will be super important to kind of answer the question of what is the role of dust? Because it's the only, going to the near infrared is the only way to disentangle what is extrinsic dust and what is intrinsic supernova properties. The Vera Rubin Observatory, hopefully we will start in 2025 and will be a complete revolution for our field, because it will be the dark energy survey, what I just showed you, but 600 times larger than that, which sounds exhausting and exciting at the same time. And so for that, we were talking about 1,600 supernovae. Here we're talking about like 50,000 and probably more. The limiting factor here will be how many redshifts we can get, spectroscopic redshifts. So it will be amazing. And last but not least, in 5 years-ish, the Roman space telescope will launch, and Roman will be mainly focused. Well, one of the main focuses of Roman will be supernova science, and we expect to see measure good supernova light curves up to redshift 3, which is a redshift range that we have never explored, and who knows what we're going to find cosmology-wise, but also in terms of like understanding how the universe works at those high redshift. So I'm going to just leave you with my timeline of exciting past and future prospects for supernova in cosmology, and I'm happy to take questions.
Hi, thank you. So for the existing test sample, are the redshifts that you showed up and others all spectroscopic redshifts?
Yes. So with the dark energy survey, we had imaging, photometry, light curves, but then there was a kind of auxiliary program called OSDES that we use in the multi-object spectrograph.
Which telescope was that?
AAT in Australia, yeah. For LSST, we will have to use foremost, like that's our holy hope.
Very cool, thanks. For this part, I actually was connecting with that piece of the timing. You really expanded on the redshifts, well, the sample and the redshift like 0.5 to 1. I was just curious if you saw anything interesting in like the evolution of the light curves in that, or did they stay pretty consistent with the redshift sample?
So you mean the modeling, like does Sol 3 breaks at those? I think it's still, so it's kind of no, the short answer is no. The short and maybe boring answer is no. I think the more we went to higher redshift, the more we realized that not having robust modeling of UV rest rate for supernova 1A, it's kind of hurting us. So one thing that I think we will need as we go higher and higher redshift is understand more how supernovae work in the rest rate UV. Otherwise, you're kind of.
Okay, we have time for one last question.
Hi, thanks. So if I understand correctly, you still don't know whether the intrinsic scatter is extrinsic or intrinsic to the properties of type 1As, right?
So yeah, our best bet is dust. It works well in describing how, specifically how the scatter increases from the bluest supernovae, less redundant one, and the highly redundant one. But yeah, it's still we have still some open questions. Like we don't know exactly where this dust comes from, for example, if it's just circumstellar dust that is locally at the supernova explode, or if it's galaxy dust. And we see that this dust works differently if a supernova is in a very high massive star forming, high mass galaxies or low mass galaxies. There is for sure some correlation between whether the galaxy is passive or start forming. And I think we still need to kind of get the very full picture. But yeah, if you ask me what are you exactly, I would say dust.
Okay, let's thank Marianne again. So our next speaker is Thales Gutcke, who is gonna tell us about simulations and early dwarf galaxies.
Hi everyone, is this on? Yeah, okay, great. My name is Thales Gutcke, and I am going to talk about cosmological simulations, but I'm actually I'm in the cosmology session because my title started with the word cosmological, but I'm actually kind of going to talk about globular clusters. So let's get into it. So first of all, for those of you who don't know me, my name is Thales. I'm named after this very hairy dude. And it's pronounced in the German way. Who knows how the Greeks pronounced it? So globular clusters are interesting stellar objects that we know mainly originally from just inside the Milky Way, but we've now detected more and more globular clusters also in other galaxies, and including ones that are dynamically associated with dwarf galaxies. And I'm going to just flash a few images of some known dwarf galaxies with globular cluster. This Fornax dwarf, it has 5, although the 5th one's not marked. Who knows? I think it's not visible on the optical. And then there's pretty much the smallest known dwarf galaxy satellite to the Milky Way with a globular cluster and a very low mass globular cluster. There's also satellites to Andromeda, like Andromeda 1 dwarf also has a known globular cluster in it. And so trying to combine cosmological simulations of large scale structure, the collapse to full galaxies, and then actually having globular clusters form or accrete into these systems has been not possible to date. And so I'm just going to show you how maybe it is going to become possible in the next few years, or kind of maybe now. So I developed a model that is called Lyra, and there's lots of galaxy formation models on the market these days. So you may ask, why a new model? So the main issue, I'm not going to go into this too deeply because it'll take too much time, is that in current cosmological galaxy formation models, how to actually accurately model baryonic feedback has been a crux of the problem for at least 15, probably 20 years at this point. And especially for lower mass galaxies, but actually for all galaxies, probably the prime feedback channel is to first order is supernova, and then the winds that come out of supernova. And we really, like in most cosmological simulations, don't resolve them well. We don't know how they cool or how they expand, and there's a lot of simplifications. So kind of the simple outset of my modeling was, how about we just resolve every supernova? And what do we need for that? And unfortunately, this requires about a 1 parsec spatial resolution cosmological simulations throughout the whole galaxy because they can explode anywhere. So that was just the benchmark where I was like, okay, this is what we need to go to. So then question 2, why study dwarf galaxies? First of all, dwarf galaxies are super interesting. They're the most frequent galaxy in the universe. And as we just heard, like the Vera Rubin Observatory is coming online for cosmology, but also going to probably expected to detect hundreds to thousands of dwarf galaxies out to like 10 megaparsec from us. So we're going to have an explosion of dwarf galaxy data in the next few years. And so as they are simple systems compared to a full Milky Way, I think they're a great thing to study. But from a computational point of view, they're also a great thing to study, because if I simulate a Milky Way galaxy with like 10 to the 12 solar masses, or a dwarf galaxy with 10 to the 9, I get like 3 orders of magnitude extra in what I need to actually simulate, or less. And so if I don't put that into the resolution elements of the simulation, then I can actually just go to way higher resolution for the same cost. So that gets me to what I'm trying to go through to for the top part. So just a quick overview of the Lyra model. Some of you from last year know this. So it's a full cosmological simulation. It retains the entire large scale structure with its merger history. It goes to these small scales. So it includes a full multi-phase ISM down to 10 Kelvin, which naturally creates molecular clouds. Once you have molecular clouds, you can collapse them and they form individual stars. In this case, I mean individual as in a star particle is a star. So we're drawing from the initial mass function of stars. Once every star is an initial star, its own star, then each one can explode as its own supernova. And as I said, we're going to a spatial resolution where we can actually resolve that expansion. Another knock-on effect then is if you have every single supernova, you can actually do the yields from the supernova more accurately and not in an integrated fashion. And finally, there's also a POP3 enrichment model where the metal seeding is not homogeneous, but in many halos in the early universe. So this is things that we've put in the model. And what's cool about numerical things in general, but this model in particular, is that going to higher resolution just provides emergent features that we didn't put in but come out for us. And so the one I'm going to talk about today is star clusters. So I don't put in that star clusters form, they form clustered, and I get to look at them. This also has a knock-on effect for feedback, namely that the supernova cluster, but very interesting if you want to talk about it. I'm happy to talk about it. I'm not going to talk about it right now. Sure. For the CGM, that's also an emergent feature. If you resolve every single supernova, then the outflows come out naturally. Okay, just to go into the supernova, because they are really kind of the core of the model. This is what a supernova looks like at the native resolution of the full cosmological simulation. This is in a separate box, but that's what they can look like if they were in a homogeneous medium. And as I said, we have individual stars. So this is the initial mass of a star particle, and we get to put in the supernova energy, the mass return, and the metal return for every star individually. Okay, why am I going backwards? Okay, just to show some movies, because it is a simulation. This is not fully relevant to the star clusters, but they're very pretty pictures. So this just gives you an idea of actually resolving the supernova explosions at high redshift, provides you with these very beautiful bubbles. And this is the morphology of these dwarfs at early times. So they're quite expensive simulations. I have currently 5 zoom-ins, and I'm just going to not talk about the redshift 0 properties too much, just to show you that we do match most of the relations. There's a stellar mass halo mass relation. Here's the mass metallicity relation, or magnitude metallicity relation compared to local group dwarfs. Here's the size magnitude relation. Up here are the Milky Way globular clusters. Down here are ultra-faint dwarfs. So actually my simulations end up in more of the classical dwarf regime. In terms of stellar kinematics, there's rotation, dispersion, and they're all dispersion supported systems. So dwarf spheroidal counterparts. Also the morphology in terms of the ellipticity seems to match the observations well. These are 5 of the star formation histories of the 7 that I actually have. 2 of them are reionization relics. That means they formed stars in the early universe and then decided to go into retirement. And then the other 3 have these ongoing star formation histories with an interesting second one that also decided to come back from retirement at some point. Cool. So what does this look like? And I'm telling you here, watch for the central starburst because there's, yeah, it'll happen. So this is a little guy, and that's the redshift up there. So this is really high redshift formation. And so the dwarf spheroidal nature of these comes out from these millions of mini mergers that happen in the early universe. Slightly later in time, there is a major merger of this system that I can also show you. And so there's a lot going on in these dwarf galaxies, even at redshift 2 still. So after redshift 2, it kind of slows down and they become more boring as they've mostly merged most of their things together. But you can already see in these images that there are a lot of little substructures flying around. Some of them have dark matter, but what I'm going to show next is finally getting to the globular clusters I promised. So one interesting thing about globular clusters from observations that we know is if we integrate all the mass in globular clusters of observed systems as a function of stellar mass of the total galaxy, we get a kind of the little power law or like a non-linear relation that's sort of potentially reminiscent of the stellar mass halo mass relation. But when we go to some property, some mass of the globular cluster as a function of halo mass of the objects, we get a pretty much a tight power law. And this has been coming out more and more as we get better handles also on the halo masses of objects. And this has been kind of a conundrum, and people point to the fact that globular clusters seem to not, form with the bulk of star formation in galaxies, but rather that they're somehow more related to the dark matter buildup of the systems rather than the further on star formation history in the later universe. So this was interesting to me, and I wanted to take a look at my galaxies, and I seem to match this power law pretty well. So this is the same line shaded region, and then the circles are data from low mass systems, and so this is also predictive from observations, and definitely also with small galaxies that have no globular clusters. So this was already an interesting aspect. And then I looked into it in a little bit more depth, and what is happening is exactly what we would think if we get a halo mass relation, namely that the globular clusters actually form with dark matter halos in the early universe. And so they are exactly following the buildup of the halo. And then what happens when we track the mass of either dark matter or stars in globular clusters over time is that they lose their dark matter, but they don't really lose their stars. And if you look at the velocity dispersions of the dark matter in blue and the stars in red, then you can understand how this is possible, namely that the dark matter is stripped during infall because it has a much hotter velocity orbits, and so they're able to be stripped. Okay, and I'll just finish with this. So this has kind of been ongoing work. I haven't published it, so yeah, but that there are multiple star formation episodes in these dwarfs, which are reminiscent of known multiple stellar populations, which do provide like wide metallicity distributions in the stars. And so I can skip over these videos and go somewhere. Thank you.
Hi, great talk. I'm curious if you can comment on binarity, if it's included in the models, if not, what impact will that have on the results?
Yeah, so binarity is known to affect globular clusters and their dissolution. And what I didn't really go into is the fact that due to the collisionless nature of the simulations, the stars the inner parts of the globular clusters aren't modeled in direct n-body. And so I wouldn't say that I trust the central densities or the profiles of the globular clusters, just the fact that they're there or not. And then, yeah, so I do have to apply a dissolution model to my globular clusters because some of them survive in the simulation that wouldn't if you account for two-body relaxation. And so I think that's where the binarity comes in, is that in that post-processing step, you could add the relaxation from binary source.
The Milky Way possesses self-gravitating blobs of gas that are massively globular clustered, but it does not form globular clusters anymore. And the reason for that, we think, is feedback. These GMCs are dispersed by feedback, and in particular, it seems that early feedback in the form of radiation and winds is necessary and sufficient to disperse GMCs. So your model doesn't include early feedback, if I understand correctly. I guess why should we consider these simulations predictive of star cluster properties if we're missing this sort of important piece?
So the globular clusters you're referring to are the young globular clusters in the Milky Way, whereas I'm comparing to ancient globular clusters. And I think the conditions in the early universe are sufficiently different that we don't know the effects. I mean, sure, every model's wrong, and many cosmological simulations with and without radiation still are missing many aspects of physics. So you can always point to missing physics and say, well, that must be the reason why these are not real. But we have to work with what we have.
Okay. Let's thank Thales again. So next we'll hear from Seiji Fujimoto, who will tell us about high-redshift galaxies from JWST and ALMA.
So, hello everyone. My name is Seiji Fujimoto, currently working at UT Austin, almost finishing the first year of this Hubble Fellow. So last year I started this program from October, so I couldn't attend this symposium. So it's very my pleasure to be here. Thanks to organizers. I'd like to start from the most important part of my presentation, acknowledgements. So after coming to US, thanks to this Hubble Fellowship program, so many new interaction, new synergy, new idea, new collaboration have happened. This enabled me to fully enjoy the research activity, resulting in the reading 6 first author papers. But you might already realize that in this collaboration, our fellowship friends like Willem, Ariane, Kartik, also involved with this collaboration, and of course these people actually help me a lot in this collaboration. And of course I haven't yet had the official team photo yet, so that I couldn't put more team photo, but for example in these days I have been also closely working together with Rohan, and also during this symposium I gearing up some JWST cycle 3 proposal idea for some lens galaxy stuff, so together with Anwar and Justin. So yeah, I would say that this first year is so successful, fruitful, but this is all owing to this great opportunity enabled by Hubble Fellowship, and also great collaboration thanks to you all. So okay, and this is also fun part from the last 1 year. So I was also shortly, just 3 seconds, but I featured in the Netflix JWST documentary film. So yeah, it was also fun part of the last 1 year. So yeah, now I finished 90% of my important part of my talk, so I can be relaxed a little. And I like to talk about what I'm doing. So here it shows my cover sheet of the Hubble Fellowship application. So the bottom line is the quest for high redshift universe, especially using JWST and ALMA. So here is a sort of a brief recap why important to study high redshift universe. So I think one important question here is why such a large variety of the universe today is just began from the almost neutral gas composed of the hydrogen gas at the beginning of the universe. And I think one key component would be galaxy formation and evolution. And in particular, early universe is one of the important epoch of the universe because initial condition always has the largest influence on how the things will go afterwards. And actually, the early galaxy has been always closely tied with this kind of fundamental question, like the development of the large-scale structure or process of the cosmic linearization or emergence of the first galaxy or black hole. So this kind of early galaxy study is very important. And including this context, I'd like to start from introducing the very great outcome from one of this JWST project program, cycle 1, called Uncover, which I have been working on. So this Uncover survey, we are focusing on one best studied lensing cluster, so-called ABEL 2744. So the survey design is at first completing the deep homogeneous near-Cam imaging to this lensing cluster, so homogeneously from 1 to 5 micron. Then this allows us to identify very rare high-redshift galaxy candidates. Then 8 months later, so taking advantage of the sufficient time to select the best candidate, we perform the systematic near-spec prism spectroscopy for this any type of exciting high-redshift galaxies. So the thanks to the great power of JWST and the leveraged by lensing effect, for example, here show the redshift 10 galaxy candidate. But a few months ago, there was an interesting report that from this galaxy, the X-ray detection is X-ray emission is detected. So this emission is not caused by post galaxy surrounding activity. So this is caused by X-ray presence of the X-ray luminous agent. And our near-spec followers nicely confirmed the spec-Z at redshift 10.01. So now we are capturing the first galaxy, first black hole, even redshift beyond 10. And this is another agent now spectroscopically confirmed at redshift 8.5. But this was an unexpected discovery because we thought that from photometric information, this galaxy, we originally have the photometric redshift solution, something like 5. But it turns out because of the strong emission line from the AGN, this photometric redshift was a little long, and it turns out redshift 8.5. And yeah, what we supplied is that very clear broad line feature detected from Balmer emission line. So this is the direct evidence of the presence of the agent broadline region. So when we calculate the black hole mass from this system and compare to some of the luminous quasars known before JWST, our new first black hole system places a very important constraint, stringent constraint on this kind of black hole mass versus redshift. So given nailing down the possible formation channel of the supermassive black hole. So these two systems now supporting the massive black hole seed scenario. But not only first black hole, we are also capturing the first galaxies. So here shows the redshift record before JWST, so 9.1. So yeah, enabled by some Arima line scan observation. But now with JWST, this kind of redshift 8 or 9, 10, and many galaxies, it's almost easy thanks to the very bright O3 emission. But even redshift beyond 10, where this kind of stroke emission line far outside of near spec coverage, but still this kind of clear alignment alpha break feature can be easily captured by this kind of spec prism power. So our team achieved the highest redshift confirmation, redshift 13.1. So this is the second most distant galaxy record so far after JWST. And when we provide the constraint in the UV luminosity function, so the abundance of the galaxy as a function of UV luminosity, and compared to this simulation prediction, so color code this showing by this dashed color line. So yeah, we cannot perform the spectroscopy for all near-Cam selected photometric candidates. So what we can provide is just lower limit, but still some of the constraint is already challenging to the current simulation model prediction. And yeah, several arguments have been discussed. So the potential initial mass function could be different at this earliest epoch of the universe, or maybe as I showed in the previous slide. Now we are getting to see the high abundance of AGN even at redshift 9. So maybe AGN might contribute to this kind of high abundance of bright object, even at redshift of 9. So I quickly overview the power of JWST, but still I believe that the ALMA or other large telescope has played an important role in this JWST era. So here I highlight two important roles obtained from ALMA, so redshift and characterization. So for the redshift, here I show the basic of how to identify the high redshift galaxy, especially using the JWST near-Cone filter. So thanks to this near-Cone filter set and this Lyman alpha break feature, we can identify, JWST can identify uniquely dead high redshift dropout galaxy candidate. But important contaminants can be very lower the dusty obscure galaxy. Sometimes also including contributed by some strong emission line. This kind of photometry can be some similar photometric feature can be obtained from this kind of lower the dusty galaxy. But this dust galaxy, ALMA can play an important role to detect this kind of dust emission. So maybe ALMA maybe eliminating this kind of lower the contaminants. And second, characterization. So the right panel shows the full ACD shape for one of the redshift 6.6 galaxy, so the ACD model. So the JWST has a nice power to characterize both ionized gas and young or stellar population. But to understand how comprehensively understand galaxy formation evolution, which generally start from gas and dark matter accumulation, then this kind of cold gas characterization or dust property will be also important. So where ALMA can play important role. So starting from this first redshift aspect, here shows the UV luminosity versus redshift before, so the HST selected galaxy summarized here. And after JWST, we very easily identify many number of high redshift galaxy candidates at redshift beyond 10. But from this plot, you will very immediately recognize there are two remarkable objects sitting down here. So this is too bright and very high redshift, so even challenging to the longitudinal model. So we had the astronomer very excited from the initial data set of this JWST data. But as I mentioned in the previous slide, and also Rohan reported from the dedicated ACD analysis and also environmental aspect, this object could be caused by some lower the strong emission line red continuum sources. So, and also another paper claims that there might be some tentative dust emission detected from this source. Although 2.6 sigma, this could be tell something. So my simple idea was, why not having short exposure to test this kind of rosy, dusty galaxy scenario for these sources. And fortunately, NOEMA and ALMA DDT follow-up accepted. So the result is that, okay, from both sources, no dust continuum emission was detected. So when we take a look at this data early this year, we are so excited that, oh, this might support the high redshift solution. But you might already know the story that after this, JWST DDT spectroscopic follow-up also performed for one of this remarkably bright redshift 16 candidate. It turns out this source is lower the redshift 4.9 galaxy with strong emission line. So it's important that this object, so no dust continuum is detected, but still this showed very red continuum slope. So this may indicate that this is very moderately dusty star galaxy or dusty AGN population. So in this JWST era, I think understanding what is this kind of faint dusty population is getting more important, and especially also constraining abundance of this kind of faint dusty population is getting more important. So in the last 1 year, I also work on the constraining the faint end of the IR luminosity function. So if you're interested, please check it out. So in the last few minutes, I would like to quickly also overview the second important role provided by ALMA, so the characterization. To talk about this, I would like to start from this discovery. So I've been also working in the ALMA lensing cluster survey, which is 100 hours of ALMA large program, homogeneously mapping the 33 lensing cluster. So I've been in charge of the data reduction and analysis, but thanks to this large data set, we identify very uniquely and brightly, strongly bent multiple image system at redshift 6. So in total, 5 multiple images have been already spectroscopically confirmed. So in the near future, Noah or Justin might be able to consider the Hubble constant parameter. But the thing is that this is an intrinsically very faint galaxy. So the low mass, so comparably low mass comparable to the local dwarf galaxy, but thanks to the strong magnification effect, like something like 20 or 160. So this is the brightest object so far known among the spectrally confirmed galaxy above redshift beyond 6. So this is very helpful to when we having the spectroscopic follow. So in the last few years, I've been leading the dedicated effort to keep getting the large telescope time, JWST, ALMA, KQLT, and I'd like to highlight this unique ensemble of IFU observation, JWST near spec, ALMA, and MUSE. So the total of 150 hours of observation now ongoing just for this single galaxy system. So the all elements, gas, stellar dust of the early galaxy will be fully characterized. And I'd like to quickly show some initial outcome from the near term. So the HST look like this. So the single disk galaxy. So the effective radius just 1 kPa. So we saw that this is a very typical galaxy, but it turns out from near term, very resolved into multiple clumps, now resolved into at least 15 small clumps. So this is a we have to think about what is the definition of the galaxy at this at this level. And but you might wonder that this number of clumps, this might be merging system or something. So, but we also have the ALMA data. So when we analyze kinematics, then this is the image plane, and the bottom panel is the source plane reconstructed. Then we can nicely see the smooth rotation velocity. So this is not caused by some complicated merging system, but supported by unordered disk. So this is the tells us how first galaxy early galaxy system look like. So the end of small, it's dominated by small star-forming clump formation via disk instability. Okay, so this is my summary. So JWST is capturing the first galaxy and black hole, but ALMA JWST also plays an important role for redshift and characterization. And thank you.
Time for questions. Okay, so maybe I'll ask a very quick question. So for the very high redshift black holes, so you measure black hole mass. So is it possible to also get the stellar mass of the host?
So it's actually a very good question. So some cases we see the source with broad line emission confirmed from JWST near spec observation is not point-like in near-term observation, which means that the host galaxy also start to be detected. So it's just a matter of contrast between the central black hole agent and also host galaxy. So if the central agent is faint enough, we can, for example, subtracting the point source, and we can evaluate the host galaxy mass.
Thank you. So let's thank Seiji again.
Thank you.
Oh, did you replace? You switched to the right.
So next we'll hear from Nicholas Kern, who will continue on the theme of high redshift universe and radio observations.
Awesome. Well, thank you. Can you hear me? No. Turn this way. How about now? All right. Wonderful. It's a pleasure to be here. My name is Nick. I am starting a Hubble Fellowship at MIT. Thank you to the organizers, the leads, the staff, and everyone who made this possible. So I'll be talking today about some of my work on 21 Centimeter cosmology, which we haven't heard too much about, and the role it's playing in our understanding of high redshift astrophysics. So I'll start with my takeaway, which is that 21 centimeter cosmology is a quickly growing field, and it's aiming to access a wide range of currently untapped cosmological information spanning both a wide redshift range and a wide range of science drivers. Even though we don't have a detection quite yet, new upper limits that we've set with the telescope that I'll talk about is already telling us new things, specifically about the heating of the IGM at high redshift with the first X-ray sources. And furthermore, I'll talk a little bit briefly at the end about the stuff that I'm going to be working on over the next couple of years to help transition us into a detection mindset and to more robustly extract this signal to do all the science that we want to do. Okay, so we've heard a little bit about line intensity mapping before. I'll talk briefly what we're doing here. We're using the 21 centimeter line for neutral hydrogen. This is the spin flip transition. The nice thing about hydrogen is that it's everywhere in the universe, and this allows us to probe structure from redshift of 0 all the way up to a couple hundred. It's unparalleled in its ability to do this. Because it's a line transition, by simply scanning up and down in frequency with our radio telescopes, we're actually probing structure in and out of the line of sight. This gives us this unique ability to make three-dimensional maps of the universe and trace the evolution as it's happening. Today, I'll be talking about 21 centimeter cosmology operating at cosmic dawn and EOR redshifts. There are a number of telescopes that are trying to do this. I'll talk about one that I've worked on and some of the stuff that we're seeing already. The first thing that we want to do is to make a statistical detection of this signal, so forming something like its power spectrum, and then relating it back to the parameters that govern the production of UV and X-ray photons and their propagation through the intergalactic medium, the IGM. Okay, now as you may be familiar with, measuring the signal is quite challenging. It's an intrinsically weak signal that is masked by incredibly bright foreground emission, something like 10 to the 5 or 10 to the 6 brighter than the intrinsic signal at the very low frequencies. This is megahertz frequencies that we're working at. This is one of the problems, is the non-thermal emission coming from our own galaxy, but the untold millions of radio point sources that dot the sky as well. The other component of this, which makes this tricky, is this the way in which this really bright signal is then modulated by a complex and a priori unknown response of our instrument, which happens at multiple levels. And this sets up this grand challenge of this very delicate signal separation problem, where we have to know both the foreground sky and our instrument through 1 part in 10 to the 5, and has thus far prevented us from cracking this problem. So to date, I'm showing you the best limits on the 21 centimeter power spectrum from redshift 6 to 11. What you can see is over the past 5 to 10 years, we've made steady progress and going deeper and deeper and more and more sensitivity. I'll note that most of these limits are not noise limited, so they're not sensitivity limited, they are systematics limited. So that's the key challenge right now that we face. And we're a couple orders of magnitude away from these fiducial theories. Now, one of the things that we hope to fix this problem is the experiment that we're building in South Africa. It's called the Hydrogen Epic Organization Array. We're building it in the Karoo Desert in South Africa, and we actually share a site with the SKA Mid Meerkat telescope. But Hera is a radio interferometer. It is 300 odd elements that are closely packed in this hexagonal format. Each dish is about 14 meters in diameter. And we observe in a frequency range that allows us to probe the IGM from redshift 5 all the way up to almost 30. And so it's a very neat complement to the kind of stuff that we're learning right now with JWST and the actual sources emerging from the EOR and cosmic dawn. So the data I'll talk about today, we took a couple years ago. This is what we call Hera phase 1. This is when the array was still just confined to this lower quadrant. We were still building the telescope. And we spent a good amount of time building our analysis pipeline around this initial data set. Now I can talk at length about the various chunks of our analysis pipeline, and I only talk about one tiny component, which is also one of the more important components, which is how we're dealing with instrumental systematics. And if you've been to a 21 centimeter talk, you might know that every telescope has systematics, especially when you're making a measurement in 1 part in 10 to the 5. The real question is, what kinds of systematics do you have, and what do you do about them? And so one of the systematics that we're dealing with Hera that we see right now are spurious couplings between elements in our array, and also coupling within the signal chain when the signal goes from our telescope to our correlator. What effect that has on the power spectrum, which you're seeing on the top right, are these blue bumps. And what you want to be measuring, at least at these sensitivities, is thermal noise. So it turns out if we take our data, we can find alternative representations where these systematics begin to naturally separate out from the intrinsic sky signals. And for Hera, at least, this a 2D 4A representation works pretty well. And so you can begin to see some of how these systematics separate out from the intrinsic sky signal in this space, and we use these custom Fourier filters to try to isolate these systematics. And that's what you see in orange is a couple orders of magnitude suppression in these features. I'll just say briefly, I worked with a couple students, and taking this further, you can take these custom filters and try to look at how to mitigate other systematics we see related to calibration, specifically from our poorly understood diffuse emission and the impact of antenna deformations over the course of an observing season. Okay, so when we all said and done, and we push this initial data set through, these pink dots are the limits that we set in 2022 roughly. At redshift 8 and 10.4, particularly at redshift 8, this is an order of magnitude improvement over current measurements, and across the board, it's the most sensitive limit to date. Now, again, we're still a little bit away from that fiducial theory curves, and that's what we hope taking more data in phase 2 will address. But it also turned out we had more data from that season. So that data was an initial data set that we looked at from about 20 nights. What you're seeing here is the number of nights we've observed as a function of where our telescope is pointing. The whole season, we had about 5 times more data shown by that purple curve. It turns out 5 times more data does not necessarily mean 5 times better limits. I can talk about why if there's interest. But we got about a factor of 2 from taking that same analysis pipeline and just running it on the full data set. So we got about a factor of 2 improvement, which is welcome because every factor of 2 is hard fought at this stage. Okay, so we're still a little bit of ways away from these fiducial limits, but we can begin to do actual science because we're ruling out part of that parameter space. And what I want to talk about is too much is the kinds of models and exactly why we can begin to rule them out, but I'll show you some results from sticking those limits into our inference package, which is a semi-numerical cosmological simulation with parameterizations for how UV photons are produced and X-ray photons are produced and propagate through the IGM. And this is one of our posteriors on some of the global properties at redshift 8. So this is the posterior on the average temperature of the IGM at redshift 8. Our prior includes information from HST UV luminosity functions, quasar absorption spectra, and the CMB optical depth. That's this gray line. And what you see there are, even with that data, there are lots of models where the IGM is really cold at redshift 8. In particular, it's all the way up against this adiabatic cooling limit. And we call these cold IGM models. And the Hera limits are uniquely sensitive to these models. So for the first time, at 95% confidence, we can begin to say that the IGM was heated by redshift 8 to at least above 13 Kelvin. Now you can turn this on its head and say, well, if the IGM was heated, we can put some constraint on the sources that were driving that heating. And so this is a constraint on the production of these X-ray sources at high redshift. If you assume that this comes primarily from a high mass X-ray binary population, which is what we think, you can begin to set constraints on their X-ray production efficiency. And again, with all of our prior knowledge, we have very weak constraints on this parameter. With the Hera likelihood, we begin to see strong preferences for more efficient production. Interestingly, that's consistent with a lower metallicity population, which is something we expect. The high universe, the high redshift universe has lower metallicity, but this is some of the first direct constraints on these parameters. Okay, so what's next for Hera? We're taking more data. The array is almost completed. We're going to be pushing down in sensitivity and up to higher redshift, which will give us the ability to probe more complex IGM heating models. But for the last couple of slides, I'll talk about some of the work I'll be doing in trying to extract more robust detections when we actually get to the phase where we're making detections. And to do that, I'll give you a high-level overview of the complicated nature of our forward model. So we have foregrounds, the signal, and various forms of interference that come into Earth. They're modulated by some ionospheric effects. They're modulated by our unknown primary beam response and the various kinds of analog and digital circuitry that we have in our front end. Now, the problem that we face are the lots of ends. There's hundreds of thousands of frequency integrations, tens of thousands of baselines, and upwards of 1 million sky pixels. That makes this complete forward model intractable if you're trying to do all of this jointly. And so generally, when we want to infer, say, the primary beam, or we want to learn about the sky or our front end, we have to assume we know every other component, which leads to biases generally greater at the level of 1 part in 10 to the 5. So the way that I'm proposing to fix this is to develop the first end-to-end Bayesian forward model for 21 centimeter telescopes. This is a kind of a confusing diagram, only to show you that we take a parameterization of as many parts of this data model as we can, and we self-consistently push them through a simulator to form a likelihood at the raw visibilities. We incorporate any prior knowledge we might have about the sky, the beam, the front end, to derive a posterior, and we can use some machine learning frameworks to very quickly get the derivatives to then optimize and sample the space. And this is kind of the ultimate goal. The speed up we get for pushing to the GPU is also very nice, factor of at least 50, and that allows some small components of the data model to be able to explore that joint posterior for the first time. And in the last slide here, I don't have any high dimensional chains where I can show you that this this works in like the full data set. That's what we're working on now, but I do have a toy model. So this, what I'm showing you here is I've populated the sky with various point sources, and I've given them a random amplitude. I've assumed a primary beam that I don't know a priori, and I'm modeling it with, say, some spherical harmonics. And I'm going to jointly optimize both the beam and the point sources to uncover some intrinsic EOR system that I put into the map. And so what you'll see is that as I step along this loss landscape, both the point sources and the beam, which are normalized to be the estimated over the truth, converge to one. And what you see is an underlying EOR map that's revealed. And the key thing here is not just the optimization, but in the future, the sampling, which will allow us to relate the fluctuations in the map that we see back to our uncertainty in the beam and the point sources. And that's that full parameter space, that exploration, which is key to building confidence in these first detections when we make them. Okay. Well, 1 minute. Okay, perfect. Well, in that case, I'll talk about why this is important. And the reason why this is important is because not only Hera would benefit from these analysis techniques, but the wide range of science that we hope to do with 21 centimeter in the future. So I've talked a little about cosmic dawn reionization, but there are experiments targeting the cosmic web and dark energy at low redshifts. And what's really exciting is that very, very high redshift, above redshift 40, 21 centimeter is a clean probe of the density field unobscured by so-called astrophysics. So if you're a cosmologist, this is the most interesting way to probe the matter density field at high redshift. A lot of modes are linear, and you can go down to very small scales and get a high dynamic range of the matter power spectrum. And in principle, this is the best way to set constraints on inflation, something like 10 to the 4 more modes in the CMB. And so there's a lot of interesting science that's coming out of 21 centimeter over the next 20 years, and it's these analysis techniques, these next generation frameworks that I think are going to unlock some of this science. So with that, I'm happy to put up my summary slide and take any questions.
Great, thanks for such a great talk. Congrats on all the results. I was curious about the plot where you're inferring that high mass X-ray countries should be contributing to reionization. So I was curious.
Yeah.
Where are you getting the information on like
Yeah.
the spectrum slope, you know, of like what this was
Yeah, so the result here is not so much that they're contributing to the ionization of the IGM, but the heating. And that's the thing that we're actually sensitive to, which is a great question, is why are we sensitive to that? And that's because of this equation here. So this is describing to you the differential brightness temperature that we actually measure, proportional to mainly 3 things: the ionization, right? If there's no neutral hydrogen, we measure no signal. The density, the denser the gas is, the more signal. But then this complicated relationship between the CMB temperature at that redshift and the spin temperature, aka the gas temperature. And what you'll see is that if this spin temperature is arbitrarily low, close to 0 Kelvin, it drives this entire thing to be very negative, but in an absolute sense, very large. And so we can set really precise constraints, well, at least upper limits on this, even with upper limits on the power spectrum, without making a detection. We can rule out models where the spin temperature, the gas temperature, is very cold, and early X-rays tend to heat the gas. And there are, like I said, there are models where, as you step along the redshift, the gas temperature may not have been heated until quite late time. So these are the kind of models that we're sensitive to, even with upper limits. Yeah.
Really excellent talk. Obviously, I'm a fan of this kind of work.
Yeah.
Can you go back to the upper limits plot?
Yeah.
So you said on this plot that current generation experiments are systematics limited, not sensitivity limited. So you're proposing basically 2 paths forward: one that increases sensitivity, which is Hera 2, and one that increases systematics, which is your forward modeling. So how would those 2 things push the points down the scripts? Either one of those things get you below the actual primordial signal?
Yeah, so I should say some of these are noise limited. The ones that are currently taking data that are taking more data are systematics limited. That's basically Hera, LOFAR, and NWA. So the key thing about the forward model is not so much that it actually removes the systematic. What it allows us to do is to understand when we see a detection, is that detection a systematic? Basically, it allows us to have an error bar that is a systematic error bar and not just a noise error bar. You may be familiar with the detection of the global signal. This was in 2018 by the EDGE experiment, and there was a flurry of theoretical speculation that this could be coupling between newly charged dark matter and the baryons, and it was very interesting stuff. Follow-up observations now indicate that was probably that detection was not cosmological. If we had had an ability to say, look, that was actually a primary beam side lobe that was acting weird against a really bright foreground, we would be able to say, we have detection, but the systematics error bar tells us that it's not significant. So we need instruments that allow us to make a detection, and then we need these analysis frameworks because there will always be low-level systematics to build confidence when we can say, okay, we have a systematics error bar and we still have a detection, right? So that's the key thing there.
Okay, so our next speaker is Sultan Hassan, who will continue talking about the Irish universe. Sultan is saying that's thanks, Nick again.
Hello, everyone. Hear me good? Yeah. Okay, right. So thank you very much for the organizers. It's been great to be here. So I'm Sultan Hassan, I'm at NYU. So I'm basically trying to share with you some of the things that really motivated me to write this letter, which we had a very nice debate when I was attending the KITB workshop in Santa Barbara for data-driven astronomy. And I had great discussion with many of the folks here. And this is mainly driven by one of the interesting trying to connect different communities, and it's also driven by the recent debate we had in the field. So let's get started. So we know winter is coming, right? So we have all this set of great experiments coming with high resolution and large scale, right? And I think now we are really probing this high redshift regime, and it's very interesting now to start to think about how we combine different bands and different experiments together, okay? So we know that we are really extremely excited, especially if you are like doing high redshift science, right? We are really excited about AWST, right? Because as you see here, this is one of the papers, early science release. This is the magnitude as a function of redshift, right? All the gray points, this is all the HST results, but all these red symbols really pushing things to high redshift. And this is really very exciting to us because now we are starting to probe the time when the first stars coming in, right? There have been interesting debate in the field about the challenge to the theory, right? So this is here some comparison between the luminosity functions at a redshift of 10 and 13, where several models, semi-analytical or cosmological or scaling relations, they kind of fail to reproduce these bright objects, right? So that's a challenge to the theory, and it has been really a big debate in the field. But then whenever you have a tension, right, maybe it's a way to get some new physics, right? So whenever there is a tension, like your theory is not really reproducing the observation, then there is a tension, and to resolve that tension, maybe you always think you have maybe 3 different directions in astronomy to think about. So you could blame the measurement, as Nick was saying, and then you can say, well, maybe there is systematics and the estimates of the redshift as has been shown by that detection of redshift to 17 found to be redshift to 15. So there are many uncertainties in the measurements. You could also blame the astrophysics and say the measurements is okay, and maybe you need like exotic sources, or you need to change the IMF, or maybe you want to do some dust. But then someone else can say, no, let me just invoke my favorite dark matter scenario and then just change the dark matter cosmology, because all these are really degenerate between each other, right? Right. So once you hear this debate, right, I'm coming actually from the 21 centimeter cosmology before I started to learn galaxy formation. So I started to remember the same debate that we had in edges detection. So we had the global signal detection of the edges, and also it's found to be one of like it's very deep, deeper than the theoretical model. And then you can also have these 3 different directions to put your blame on, right? You can say the measurement is wrong, and that was what's been done, is that like some papers came in and found that maybe it's a pure systematics, or maybe you need something to make the IDM very cool, and then maybe you can add some interaction to baryonic dark matter Romeodian magnetic field. But what was very interesting to me between the debate we have between detection in the AWST and the models and the detection of this signal with the theoretical model is that you always need to use the same astrophysics arguments to resolve the tension in both of them. And that's what I started to think about. Maybe there is something we can do here, right? There is something we can combine these 2 experiments together, which is something I don't think has really been received lots of attention in the field, which is very, 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 I think extremely interesting, that you always need 2 efficient star formation, either to match the luminosity functions that are measured by AWST, or maybe to resolve the tension you have in the detection. So this is just a quick summary. I mean, you have seen this a lot. This is just like how the global spin temperature, but I want to connect these together. So the connection here, we are interested in the beginning of the signal, and that signal comes actually just you have first star. So in the beginning, you don't have any signal because the spin temperature only mixes with the CMP, right? And then once the first stars come in, they emit Lyman alpha photons, and this Lyman alpha photon goes and decouple the spin temperature from the CMP, and then you start to see that signal. So we are interested in, so this is how you can really combine these together. This is just like measurements of UV or infrared, and with different measurements in the radio side. So the question I have been very interested to answer is that, can galaxies detected by JWST, right? These bright sources that we have seen in the early universe, would they really provide enough Lyman alpha photons to cause a 21 centimeter signal as claimed by the edges? Because the edges said maybe at 17. So the question is that, can these galaxies that we really detected in these high redshift can really do that, right? And because, as I said, I mean, they emit light, they decouple the spin temperature, right? So we need to look for some quantity to estimate these things, and one of the least biased quantities may be the UV density, right? So this is the evolution of the raw UV density as function of redshift. So basically, the way you do that, you go to the measured velocity functions, you integrate them down to some certain some threshold, right? And then for this plot here, we are using I'm showing just like -18, and I'm asking this question, right? So what you see here in these faint symbols, this is all HST data, all the bright ones here, like, or the more bright symbols here, like the magenta and the green, they all from JWST. The error bars coming from the cosmic variance, if you account for cosmic variance, or if you account for the uncertainty in the fed end to the velocity function. And what you see here in this box, the red box, is that this is the minimal amount of raw UV needed, like just this, if you assume theory, just a simple theory, pen and paper, like how much really raw UV we need in order actually to cause a 21 centimeter, in order to detect a 21 centimeter at that particular redshift. So integrating down to -18, what you see here, there is, as we know, that there is this rapid evolution in raw UV, that it gets very hard to satisfy this with this red box, right? So maybe unless you have somehow an evolution that is growing very rapidly, and then kind of a flat evolution, right? So maybe looking at this, this is not realistic. You can't really reproduce this maybe by a simple physics, and maybe the answer is no, if we integrate down to -18, right? So what happens then if we integrate down to -13? Because we expect in high redshift we should have detection of more these faint objects, and maybe the sensitivity of JWST also can go to -13. So if you integrate down to -13, right, you realize that just a simple linear function or power law between the raw UV and redshift can really match this vector, right? So you can reproduce that very well by the prediction, and of course the uncertainty will be higher because now you are going to much more in the faint end. So the answer is yes. So most of the galaxies that have been detected in JWST now, they could really reproduce. They could really, if you extrapolate down, and hopefully in the future observation, we can really get more measurements to see whether we really have enough photons to cause a 21 centimeter signal at that time. But then you can also have more fun, because people have also, when they work on the radio side, people have said, okay, maybe there is not only the CMB, there is excess in radio background, and that excess could be actually maybe like from black holes or from other sources. So the question is that, can JWST, so that's another question here, is that can JWST really provide constraints in this background excess, right? So you can consider the background excess by black holes, and if you do the calculation of the black holes, people found that maybe this would boost your minimal constraint by a factor of 3 up to the brown box here, and then you can do a single fitting, and then you realize maybe, well, because I mean we don't know the evolution of raw UV at high redshift, right? So you're looking at the uncertainties, and here maybe just a shallower evolution in the raw UV could really reproduce this very well, right? So then the answer is still yes. We can. I mean, this is very exciting. It's very exciting to see that like JWST could actually provide independent constraints in the excess of the radio background at these high redshift, right? Then you can consider radio excess that has been detected by that experiment, RK2, which is they have detected a very strong radio excess in high redshift, and taking their spectra and calculating the boosting factor, you realize on top of the minimal constraint, you need to multiply that by a factor of 20. So it's a boost by a factor of 20. But then what is interesting here is that given the large uncertainty, you realize that once you boost it, you boost everything by a factor of 20, you're already in the same level of the measurements at low redshift. And then maybe the evolution is just flat. Maybe just a flat evolution in rho UV could really reproduce that, and the answer is still yes, right? So what I'm trying to show here from here is that from all these different lines here is that we don't know the evolution of the rho UV, but the rho UV could capture many interesting quantities that is not only relevant to galaxy formation, but is also extremely important for, it could really constrain the level of the background excess we expect. It could tell us when really you can expect a 21 centimeter signal. And then you can actually use, so here using like AWST to do something to 20 centimeter, but we can also use these to do something to AWST. So then we can actually take these constraints for the rho UV, if you assume excess, and if you don't really assume excess, and then you try to predict what is the form of the velocity function you need in order to have enough sources, they emit enough photons so they can decouple this, the spin temperature, and then you have a signal, right? So then you can have fun with that. You can just assume Schechter form and you compare with the measurements, and hopefully with the future observation, we can discriminate between these different measurements and different at high redshift. So with that, I wanted just to highlight the summary here is that I think we started to begin in a place where we should really start to connect communities and experiments together to place tight constraints. And I think it's just here, it's a very interesting game between AWST, which can really place independent constraints on the radio by experiments, and also radio experiment can do the same for AWST. Thank you very much.
Sultan Hassan, we have time for questions.
People hungry.
Maybe I'll ask a quick question that people are thinking about more. So in terms of the edges signal, is there any funding effort to reproduce with an independent instrument, or what's the future?
Yeah, I think there are some experiments coming. I think like the SARAS experiment is trying to do this. I mean, in the beginning, they revised their experiment and they used the same edges data, and they found no detection. But I heard recently that they have some new measurements coming soon. Yeah, so there are some experiments coming. Yes.
That's very cool stuff. Just a quick question, and maybe you said this. So you're looking only at modeling, will these sort of particles have Lyman alpha photons to couple the spin temperature to the gas,
Right.
not so much what is causing the very cool gas temperature per se.
Yeah, no.
Okay.
No, but that you can also depend on the model, right? You can model that in the model, because here we are assuming just a simple population star, 3 stars models, but you can use any model. But I think the most important thing here is that you always need for independent constraints from different experiments, right? But I think looking at the rho UV, it's a very interesting quantity to combine these.
Okay, so let's end the session here. Let's thank all of our speakers. We'll be back. We'll be back at 2 p.m. Yes.